So I'm going to change my share, and we're going to talk a little bit about Schrodinger's atom, okay? Schrodinger's version of the hydrogen atom. I think there's like a umlaut or something over the E, but I'm not sure. So for Schrodinger's hydrogen atom, he said, you know what we're going to do is we're going to treat the electron as a standing wave. Can you see all of this okay?
Yeah.
Okay, good. So we talked about this yesterday, where if this is the proton in the hydrogen atom, you think of the electron as a standing wave like this. Okay. And because it's a standing wave, the wave, the equation, or what's called the wave equation, has the symbol psi. Which looks like a pitchfork. And that does look like pounds per square inch, but it's psi. Mm-hmm. So we treat them as standing waves, and that's called the wave equation. And when you have the standing wave, that means that only particular solutions are allowed to the wave equation. Now, the other thing that we need to know about psi is psi depends on three variables. And those variables are n, which is the principal quantum number, L, which is the angular momentum quantum number, and M sub L, which is the magnetic quantum number. And although they are not equal to, the way to think about these three variables is like X, Y, and Z when you talk about an equation in 3 dimensions. Okay? So X depends on these three variables, N, L, and M sub L. And again, because of the standing wave, you can only have specific N's, specific L's, and specific M sub L's. So here, back to this, standing waves, only particular solutions possible for psi. That means that you need to have specific combos of N, L, and M sub L. Specific combinations. And so what we're going to do is we're going to talk about those combinations and what N and L and M sub L essentially mean, okay? Okay, so I'm going to put, this looks like an amoeba, doesn't it? With a little nucleus or something?
Yeah.
Okay, so let's talk about the principal quantum number. The symbol, of course, is N. And essentially, this tells you the energy of the electron. Also gives you a rough idea of how close it is to the nucleus. And really, we're talking about the region where the electron is likely to be found. Now, I want to talk about that region likely to be found. It's kind of like talking about me and Eureka. I'm usually going to be found really close to the house, right? But I could be found anywhere in Eureka at any given time. So likely is, not, this is where it's going to be. And the problem, of course, with finding out where an electron is how do you find out where an electron is in an atom? I mean, how do you do that? And the answer is you have to find it. So how do you find it? Well, you have to, the best way to envision is if you were to close your eyes right now and pretend you'd never been in that room before, how would you find out where the walls are without moving? You can't do echolocation because you're not a bat. But could you pick up something and throw it in front of you?
Yeah.
And you could listen for how long it takes to hit the wall, and that would give you an idea of how far away the wall is, right?
Yeah.
And you could throw something to the left, to the right, and even up above to find out if you have a cathedral type ceilings or something, right?
Mm-hmm.
So you would throw something at the wall. Now, would you throw a truck at the wall?
No.
The answer is no, because it would move the wall, right?
And I can't throw a truck.
Well, let's pretend you could throw whatever you wanted because you're super person. So the idea here is you want to throw something at the wall that's small so it does not move the wall, right?
Mm-hmm.
Well, what are you going to throw at an electron that's smaller than an electron? The answer is there's nothing you can really do. You could throw photons there, but photons are too small to measure individually. So you do send energy at the electron, but guess what happens as soon as you hit the electron? It moves. So you can probe where the electron was, but now it's moved because you've hit it. And wherever it's moved to, that's not where it would have been anyway. It's moved there because you hit it.
Mm-hmm.
So it's a tough thing to find out where the electron is. But if you do this enough and you hit it, you get an idea of where it was. And if you map that out, you get an idea of where it's likely to be. Okay? So that's what this is, the region where it's likely found. Let's see, the allowed values of N are N equal 1, 2, 3, essentially up to 7. And these are called shells. So you've got the first shell, second shell, and so forth and so on. These shells are shaped like a sphere. And you're likely to find the electron somewhere in that sphere. So if I were to draw my little nucleus here, and then I were to draw the N equal 1 shell, it would look like this. So what is that little guy there?
Where the electron would be?
No, that's the reflection of light off of the sphere.
Yeah.
So that you think it's three-dimensional.
Okay.
So that means you could find the electron somewhere in this region. Okay? And here's the N equal 2 sphere. So for the N equal 2 sphere, where are you likely to find the electron?
In that
in that region there, which overlaps with the n equal 1.
Oh.
You see what I'm looking at here?
Yeah.
So this is going to give us some interesting things to think about later on in chapter 7. So if I were to draw the n equal 3, what would I draw here?
Another shell.
And where would I draw the arrow?
From the shell to the nucleus.
Right. And I will tell you this, that when you look at these for the n equal 2, you're more likely to find it out here farther away from the nucleus than close. So if we were to draw kind of like a, here, this is the n equal 1, you draw something like this. So where the thing is high, you're likely to find the electron.
Yeah.
And where it's low, you're less likely to find the electron. And this is the distance from the nucleus. So you see how, roughly speaking, whoops, this lines up there.
Yeah.
So I don't have the whole tail there, because when we draw the n equal 1 sphere, we say, okay, let's draw the n equal 1 sphere where we're going to find the electron 95% of the time. And let's not worry about the other 5%. Now, if I were to draw the n equal 1 for the 100%, so this goes all the way out to infinity, right? So if I were to draw the shell based on the 100%, that shell is called the universe. So that's why we don't do the 100%. Every shell would be the universe. So that means that every atom in you, the 100% shell is the universe. So, you could get all philosophical about this if you wanted to and say, well, you know what? The 100% shell for everybody's is the universe. So we are all the same, kumbaya. But we're not going to go there. We're going to go with the 95% so that we can use this as a model.
Right.
Everyone being the universe is not a very good model, unless you're trying to make money off of weak people.
Do we need to be comfortable with drawing these plots?
No, you do not. Now, let me show you the n equal 2. So I'm going to go up here. This is what the n equal 2 looks like. So can you see the n equal 2 goes to, right here? Boop, 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 boop.
Yeah.
And this is the 95%. But where are you more likely to find the electron? Close to the nucleus or farther away from the nucleus?
Farther away.
Right, because it's a taller hill. And guess what the n equal 3 plot is going to look like?
3 peaks.
3 peaks.
Larger, farther away.
And how large do you expect those peaks to be relative to one another?
They would get progressively larger.
Bingo.
Kind of.
So it would look kind of like this.
Yeah.
Progressively larger. You nailed it. And that's the way it looks for every one of these. So that's the principal quantum number. And the big ideas here, well, there's a lot of big ideas. They're called shells. They're shaped like a sphere. Gives you a rough idea of how close to the nucleus. And here's something else we're going to say. Psi squared gives the probability map. So what's the probability map? These guys. So this is psi squared right here. This is psi squared for n equal 1. This is psi squared for n equal 2. This is psi squared for n equal 3.
Okay.
Okay? Okay, so now let's move on to the angular momentum quantum number. So I want to do this similar to what I had just done. So I believe I started with the symbol first. The symbol is L. And this kind of gives a more specific location for the electron.
Subshell?
Yeah. But I'm really trying to copy this guy right here and kind of do them in the same order.
Right.
Gives a more specific location and energy for the electron. The allowed values depend on the value of n. So, for instance, if you have n is equal to 1, L can be equal to 0. If n is equal to 2, L can be 0 or 1. If n is equal to 3, L can be 0 or 1 or 2. And for 4, 0 or 1 or 2 or 3. And basically we max out at 3. So if n is equal to 5, it's 0, 1, 2, or 3. 6 is really 0, 1, 2, and 7 is 0 or 1, essentially.
Why? Because can't n go up to 7?
It can, but for 7, L is only usually equal to 0 or 1 because we don't have enough atoms to describe that big of a shell.
Okay.
You'll see later, but right now we're just going to go up to 4 because it's very simple. 0, 0, 1, 0, 1, 2, and 0, 1, 2, 3.
So L stops at 3.
Pretty much, yes. Now, these numbers can be confusing. So people give letters to these. So this would be S, S or P, S or P or D, S or P or D or F. So 0 corresponds to S, 1 corresponds to P, 2 corresponds to D, and 3 corresponds to F. And you need to know that. And you need to know the order, that it's SPDF. So you need to think of a way to remember those 4 letters in that order. So what are those things called where you have letters that represent something?
Mnemonic.
Mnemonic? So some people do fine when they try to figure out a mnemonic for this, and some people don't. And that's my mnemonic.
Okay.
Some people do fine.
Right.
Okay. You could probably think of something more clever, but it works for me. It's my gift to you if you want to use it, and you don't have to. I don't feel bad. Okay. So these things, the L's are called subshells. And something else that you need to know is they're all spherical. And you also need to know the energy of each one. An S is more stable than a P, which is more stable than a D, which is more stable than an F. So when we talk about stability and we look at potential energy here, this would be a 4S is more stable than a 4P, which is more stable than a 4D, which is more stable than a 4F. So here, potential energy, an F electron has more potential energy than an S electron in the same shell. we're going to go back to this. When we talk about stability here, 1 is more stable than 2, 2 is more stable than 3, 3 is more stable than 4. So if we do the ends, here's 1, here's 2, here's 3, here's 4, and so forth, where this is a potential energy. Okay, so, this is your go-to, first of all. Is it in the first shell or the second shell? That'll tell you which one's more stable. Well, what if they're both in the same shell? Well, then is it an S or a P or D or an F? That'll tell you which one's more stable. Okay? And these also give the orbital type. And the other thing I'm going to say here is that they are made of orbitals. Just like shells are made out of subshells, subshells are made out of orbitals. Okay. Go ahead, I'm sorry.
Nothing.
Okay. So next we go to M sub L, the magnetic quantum number. And that's M sub L. Oh, actually, I shouldn't put that there. I should put that here. The symbol is M sub L. This gives a more specific location for the electron. The allowed values depend on L. So here I'm going to make L values. If L is equal to 0, so if L is equal to 0, we're talking about an S subshell that is shaped like a sphere, okay? M sub L can have the value of 0. If L is equal to 1, M sub L can be -1 or 0 or +1. Now, this value here tells you this is one orbital. When you have a -1, a 0, or a +1, that's actually 3 orbitals. Now, when L is equal to 2, what are our allowed values? -2, -1, 0, +1, or +2. So do you see that the range basically depends on L, and it goes from -L to +L?
Yeah.
Okay, so what do you think the values are allowed for L equal to 3?
-3, -2, -1, 0, +1, +2, +3.
Okay, so if this is one orbital and these are 3 orbitals, what is this?
5.
5 orbitals. And what is this?
7.
Okay, now remember the L tells you what's allowed for the M sub L. I'm going to go back to these L's. This is S, P, D, F. And also back here, I told you that these give you the orbital type, right? SPDF gives you the orbital type. So let me show you what the orbitals look like for an S, a P, a D, and an F. Now remember, for the S, there's only one orbital, so I'm only going to draw one thing. For the P, there's 3 orbitals, so I have to draw 3 of them. For D, there's 5 of them, so I have to draw 5 of them. I'm not going to draw the Ds because they're really hard to draw. And the Fs, forget about it. I'm going to pull a book up or a picture up from the book and say, Here's an F. Okay?
So in lecture, you said that we need to know how to draw S and P's.
Absolutely. So let's look at the orbital type. So there's an S orbital, and it looks like this. It's a sphere. And there's only one of those. What does a p orbital look like? A p orbital looks like this, kind of like an infinity sign, and that's the nucleus. So what is this shape here supposed to be? It's the shape where you're likely to find the electron if it's in a p orbital. Remember, Schrodinger's equation is about the energy of the electron and where it is. Now, this is one of the p orbitals. This one's called the px. Now, here are your Cartesian coordinates, x, y, z. So do you see how the px lines up across the x-axis?
Yeah.
What do you think the py is going to look like?
Across the Y axis, so up and down.
You got it. Now, what's the pz going to look like?
Kind of diagonal.
Kind of diagonal, but you got to remember, since it is coming out of the paper like my pen is here,
Yeah.
this part of the p axis or p orbital that I have my finger towards, because it's closer to us, it's going to look bigger.
Right.
So you draw something like this. Now, what happens when you combine all of these together? It looks like this.
One big thing.
One big thing.
Yeah.
So it looks like a sphere. When you put those three globs together, you get a sphere. Now, I'm going to give you an idea of what one of the D's look like. Well, actually, four of them. Four of the D's look like this. I call it a four-leaf clover. And just like the P, X, P, Y, and PZ, the D's have different orientations. So you have one four-leaf clover that's flat, one that's kind of up, one that's twisted a little bit. You've got all different orientations. And then you've got what I think is the coolest looking D orbital. It looks like this. It looks like a p orbital with a life preserver around it, which is really pretty cool looking. So what does this shape represent?
The orbital type.
The orbital type, but also, I mean, the big picture. What does it represent?
The location of the electron.
Where you're likely to find the electron in this particular type of a d orbital. And here, this represents where you're likely to find an electron in that d orbital. And what is really interesting also is that here, this looks like one orbital, right?
Yeah.
This looks like two orbitals, but it's not. It's one orbital. This looks like four orbitals, doesn't it?
Yeah.
Or maybe two P's that are combined together, but it's not. This is one orbital. And the really cool thing about it is this is the nucleus. You can't find the electron in the nucleus. It's not there. So when you look at these orbitals that are like this, how could the electron get from one side to the other when it can't go through the nucleus? And the answer is, well, for goodness sakes, this is just a model. It's not real. So get over it. And in fact, because we don't know where the electron is at any one time, you can pretty much say that the electron is everywhere, right? It could be at any place in this orbital. So it's kind of like, maybe the electron is like the god of atoms because it's everywhere. All right. So these guys, I don't expect you to draw, but do I expect you to be able to draw what looks kind of like an infinity sign?
Yeah.
You bet your bippy. How about a sphere?
Yeah. I'm wondering how you would make this more complicated for an exam though.
Oh, well, who knows? Who knows? But I can tell you there's not going to be a question that says draw a p orbital and it's worth 10 points.
Yeah, so I was thinking it'd probably be part of a question.
Probably part of a question.
Okay.
Okay, so that's orbital type, which goes to magnetic quantum number. So there are some questions in your book that are based on this that maybe we can look at now that we have a little bit of an idea about Schrodinger's hydrogen atom, okay? So this part of the chapter is really just about accounting, making sure you know what the ledger is asking you about and supplying the answer. Okay, so here we have the section on quantum mechanics. This is on page 304 if you have a hard copy.
Mhm.
And I'm trying to zoom in a little bit. Actually, I don't want to zoom in too much because if I do, I'll just have to zoom out later. So 27A, if n equal 4, what are the possible values of L? So 27A, for n equal 4, question mark L. Well, one of the tricks that I didn't tell you about is this, that the number of L's is equal to the shell up until 4.
Right.
So L could be equal to 0, 1, 2, or 3. What do you think the most common mistake made here is?
Well, I just forgot 0.
That's the most common mistake. You don't start counting at 0.
Right.
So you've made that most common mistake and hopefully you won't do it again.
Right.
So B, when L is equal to 2, what are the possible M sub L's? So when L is equal to 2, what are the M sub L's? So for the M sub L's, remember, you start at -2 and you go to where?
+2.
So what are the values?
-2, -1, 0, 1, 2.
And I like to designate them as +1 and +2, so it's easy to distinguish between negative and positive.
Okay.
So I'm going to change these questions. What if n is equal to 1? What can L be equal to?
For A, 0.
Okay, that's it. So what if L is equal to 0? What can M sub L be?
0.
That's right. Okay, let's look at C. For a 4s orbital, what are possible sets of N, L, and M sub L?
So N is 4, L is,
Okay, N is 4. How do you know it's 4?
as it tells you,
Because it tells you. So what is L going to be equal to?
0.
0, because S equals a 0.
Yeah.
What's M sub L going to be? What are the
0.
possibilities?
0.
Why only 0?
Because it's M sub L is plus or minus L.
And L is 0. So plus or minus 0 is plus 0 and minus 0, which is 0. So D asks us for a 4f orbital. What are the N, L, and M sub L?
So N is 4, L is 3. So that means M sub L is -3 to +3.
Be more specific.
-3, -2, -1,
0,
0.
+1, +2, and +3. So when we look at this set here, we're looking at a 4, 3, -3, a 4, 3, -2, 4, 3, -1, 4, 3, 0, 4, 3, +1, 4, 3, +2, and a 4, 3, +3, right?
Yeah.
Well, this is an orbital. This is a 4f orbital. Guess what this one is?
4F,
A 4f orbital. Guess what this one is?
4F.
And what is that one?
They're all 4F.
So what we have here are a set of quantum numbers for each 4f orbital.
Okay.
Okay. And so here we don't have any other combinations, right?
Right.
So what does that mean about the number of 4f orbitals that are possible?
There's 7.
There's 7. Just like here, this is a really boring set because this is a complete set for the 4s, a complete set.
So
So
for
how many orbitals do you see there?
1,
1. So this is a 4s orbital. And in your 4s subshell, how many orbitals do you have?
1.
1. So the 4s subshell has 1 orbital. The 4f has 7. What would your guess be about a 4p?
5.
3. SPDF.
Okay.
So the reason it has 3 is because it goes -1, 0, +1.
Right.
Okay. And the D would have 5.
Okay. So 1, it increases by 2.
Yep.
Because
It's it basically goes odds. It's odds, right?
Yeah.
1, 3, 5, 7.
Yeah.
Okay, so that's 27. Let's go ahead and do 29. A possible excited state of the hydrogen atom has the electron in a 4p orbital. List all possible sets of quantum numbers for this electron. So basically 29 is list all sets of quantum numbers
Okay.
for a 4p.
Okay.
for a 4p electron, essentially. Are you done?
Yeah.
Okay. What is n equal to?
4.
Because the number in front is the n.
Right.
What is L equal to?
2.
If it's a P, are you sure it's a 2? Would you bet your bippy on it?
Oh, no. It's a 1.
Okay, so S, P, D, F. Where do we start counting?
0.
0, 1, 2, 3. Good thing you didn't bet your bippy. So we're going to say it's a 1 because it's a P.
Right.
Now, what can n sub L be equal to?
-1, 0, and +1.
Okay, so how many orbitals are these?
3.
3 orbitals. We're going to learn later that there is an additional quantum number.
Yeah.
It's called magnetic spin quantum number or spin quantum number.
Yeah.
And we'll be learning about that in the next chapter. And so here, when they say list all sets of quantum numbers for a 4p electron, turns out that there are 6 sets. And that's because that each one of these orbitals can have a magnetic spin quantum number of either +1/2 or -1/2.
Up or down, right?
Right. And usually we say +1/2 is up and -1/2 is down.
Okay.
So the up or down is really akin to the S for an L, for an L equals 0 orbital. We call it an S.
Mm-hmm.
An arrow up is instead of writing +1/2.
Okay.
Okay. So when we talk about the number is +1/2 or -1/2 for spin. And the representation is an arrow up and an arrow down.
What +1/2 and -1/2 of what though?
They're just values that they came up with. It's based on the electron actually spinning. And when it spins, it makes a magnet. Spinning electrons are magnets. And you know how a magnet can have a north pole and a south pole?
Yeah.
So if it's spinning in the opposite direction, you get an opposite magnet. So up down is a magnet with opposite directions of the poles.
Okay.
Okay, so you can think of the up being a north pole and a south pole, north on top, south on the bottom. Down would be the north pole on the bottom, south pole on the top.
Okay.
Okay. But again, that's chapter 7, so we're kind of getting ahead of ourselves. Here, I don't think we need to spend a whole lot of time writing out answers here. We can just talk about some answers, right? 31. How many subshells are in the electron shell with the principal quantum number n equal 4? Well, for n equal 4, can you have L equal to 0?
We could have 3 subshells.
And what are their numbers?
0, 1, 2, 3.
Okay. And why can't you have a 4?
Because L is n-1.
Right. L can be all the way up to n-1, starting at 0. What are their letter designations for those subshells? In order from more stable to less stable.
SPDF, right?
Correct.
Okay.
SPDF. Some people do fine.
Mm-hmm.
Okay. How about 33? Explain briefly in 2 different ways whether or not these are possible. A, why is this not a possible set?
Because L has to be 1 less than n.
So we could answer this from two ways, right? You could say, well, for this particular n, the maximum L is 2, right? Oh,
Well,
excuse
that-
me. The maximum L is 1. My bad.
Yeah.
So your confusion was warranted because I was confused myself. For this n, the maximum L is a 1, right? You can have a 0 or 1.
Yeah.
Or you could say, for this L, n has to be at least a 3, or it could be a 4 or 5, right?
Right.
So that's what I'm saying. You can answer this two different ways and still be correct about what's wrong with it.
Okay.
So why don't you try that for B? What's wrong with this?
M sub L has to be 0. Because
So
L
what you want to say is if L is equal to 0, M sub L has to be 0.
right.
But what if M sub L is minus 2? Then L has to be at least 2, right?
Yeah.
Or it could be 3.
Right.
So I'm trying to get you to look at this forward and backwards. Why is 3 okay if this is a minus 2?
Because M sub L is plus or minus L.
So that means if it's a 3, it could be minus 3, minus 2, which works for this one. Fair enough?
Mhm.
Okay, so try and answer C based on two ways of saying, here's what needs to happen if this is the case.
If L is 0, then M sub L has to be 0.
Okay,
And the n equals 6 kind of throwing me off.
well, you don't need to worry about that. If M sub L is 1, what does L have to be? At a minimum,
1,
1. Or,
0, or minus.
no, L can be 1, or 2, or 3.
Right. Okay.
Okay, so this is something where you want to be able to look at it from both ways.
Mm-hmm.
Fair enough? If you can do that, and you're having a little bit of trouble with that, if you can do that, you will start to understand this even better.
Mm-hmm.
So here, which ones are valid? Is A valid?
No.
Why not?
Well, if n is 3, then L has to be 1 less than that.
Okay, but what if L is 3?
Well, then n sub L,
If L is 3, what does N have to be?
4,
Or 5,
or 5, or 6,
or 7, right?
7. Mhm.
So we're doing some more of this, looking at it from both ways. How about B? Is that a, it's good?
Yeah, that was good.
It is good. How about C?
L can't be more than 3.
L can't be more than 3. Actually, this one we'd have to say based on the rules they give us, it's okay, because L has to be 1 less than, but this guy doesn't really exist.
Okay.
It's a theoretical set of okay quantum numbers for electrons that don't exist.
Okay.
How about D? And I wouldn't give you something tricky like that on the test, but how about D?
If L is 3, then M sub L can't be -4.
What is the lowest it can be?
-3.
Okay, so M sub L is 2 negative, if you will, right?
Right.
Okay, but what if this one's okay?
Then L has to be 4 at
Then it
least.
has to be 4, and then N has to be
5.
And that's the way you would kind of look at it from both ways.
Okay.
Okay, so we're at 11:07. I think we've done some good work here. I want you to see here when I back away from this, that we're doing these questions here, and next are the general questions, which means that they're from any part of the chapter. Now,
Right.
I'm going to point out something to you here. Do you see these questions here that say how many nodal surfaces?
Yeah.
I don't talk about nodes because I don't think they're that, essential for your understanding of quantum mechanics at this level. And so we wouldn't worry about this. But just so that you understand what a nodal surface is, I'm going to give you a description. Because, maybe you want to know. Oh, I have to pause for just a moment. Someone's knocking at the door.
Okay.
We know you weren't picking your nose.
Okay.
Okay, so do you remember how we have a p orbital? And it looks like this. This is your px.
Mm-hmm.
Okay, so if I draw the Cartesian coordinates and put my P right here, like that, this is a nodal surface. So surface really means a plane.
Mm.
And I don't mean like plane as in plain Jane, I mean as in a two-dimensional structure that's flat.
Like an anatomy.
Yes, like you're doing a section, right?
Yeah.
So that's a nodal surface. And if you have a p orbital that looks like this, your nodal surface is right here. Right, it goes up and down.
Okay.
This is a horrible drawing, but I'm not an artist. This one actually turned out okay.
Yeah.
And if you have this one, the nodal surface is real easy. It's just right there. It's straight up and down like you're looking at a wall. Those are nodal surfaces. So what is your nodal surface going to look like for something like this? And the answer is you're going to have one right here. And you're going to have one right here. You have two nodal surfaces. Are you with me there?
Yeah.
And do you remember this guy here? Looks like what are your nodal surfaces here? Your nodal surfaces are here. These little cones that that kind of go in between the donut and go around the lobe of the sphere. So nodal surface does not always have to be a plane. It just has to be a surface where you can't find an electron. And here's an interesting thing. This is a d orbital. How many nodal surfaces do you see?
2.
This is a d orbital. How many nodal surfaces do you see?
2.
This is a p orbital. How many nodal surfaces?
1.
And this is an s orbital. Has no nodal surfaces. So when you look at the orbital type, S, P, D, F, and you look at nodal surfaces, the S has 0, The P has 1, the D has 2. What do you think the F is going to have?
3.
3. So it's not paramount for us to understand this.
Okay.
But now you kind of see it. And I'm not going to try and draw an F orbital and show you 3 nodal surfaces. It's not going to happen.
All right.
Okay. But if you kind of want to know what it looks like 2 of these with 1 going across flat. So like that, and then like that, vertical. Okay. All righty then. I think we've done some good work, and I should probably get in my car and go because I want that second shot.
All right. Good luck.
Thank you for tuning in, and I think we did some good work here today.
Thank you.
Have a good one.
Bye.